Hi all, in this lecture video we are going to discuss the problem Floyd's algorithm, that is all pairs shortest path problem using dynamic programming. Okay. So first let me define what is the problem, that is the all pairs shortest path problem. So in a given weighted digraph, find the shortest path between every pair of vertices. So for example, in this graph you have 4 vertices. uh, 1, 2, 3, 4. So you have to find out the shortest path from 1 to every other vertices. That is 1 to 2, 1 to 3 and 1 to 4. Okay. Then you have to find out the shortest path from 2 to 1, 2 to 3 and 2 to 4. Likewise, you have to find the shortest path from every pair of vertices. That's called as an all pair shortest path. Okay. So the diagram in the sense, so it's a directed graph. Okay, so because in undirected graph you can easily find out the path from one, because that vertex v of edge v of I comma j is obviously equal to v of j comma I, but that is not the case in the case of directed graph. Okay, so the next, what is the core idea behind in this algorithm? Because we are going to solve the problem by applying the algorithm design technique dynamic programming. Okay, so in the previous video we have discussed about what is the concept of dynamic programming, because in the dynamic programming, first thing is we have to solve the sub-instances, that is which is applicable for solving a overlapping subproblems. Solve the subproblems and store the results of the subproblem in the table, isn't it? So the core idea behind in this Floyd's algorithm is you have to construct a solution through series of matrices, that is D0 to Dn, using increasing subsets of these vertices allowed as intermediate. That is, first you have to construct the distance matrix, that is D0, which indicates that which uses no intermediate vertices. So that matrix indicates that there is a path from direct I to j, that is vertex I to j. The next you have to construct D of 1. Okay, which means that again you are finding the distance between every pair of vertices, but it is maximum use of one intermediate vertices. Okay, then the next D2, which means that again you are finding the distance between each and every pair of vertices by using the maximum of two intermediate vertices, and so on. Okay, in this case, in order to construct the value of D of 1, you can make use of the previous matrix, that is D0. Same way, when you are going to construct what is the value for D of 2, you can make use of D of 1. So that is the core idea behind in this. In each and every iteration, you have to construct a matrices, okay, by make use of that previous value of that matrices. That k value indicates that which will use maximum that k as an intermediate vertices. So for example, our aim is you have to find out what is d of I comma j. Okay, so in order to find this, what we are using, we are going to make use of the previous matrix, that is d of k minus 1 ij. Okay, so what is that required recurrences? So either which may use this k intermediate vertices, no. So d of k minus 1 of ik plus d of k minus 1 comma k comma j. Our intention is you have to find out the shortest distance between I to j. It will use maximum of k as an intermediate vertices. So you can consider either the minimum of this value or by adding these two, whichever is minimum, that is going to be the new distance of I comma j. So this is what that required recurrence. So on the kth iteration, the algorithm determines shortest path between every pair of vertices ij that use only vertices among 1 to k as intermediate. So that's what I hold. In order to find out d of k is an intermediate. I comma j, minimum of this value d of k minus 1 I comma j, or by adding these two intermediate vertices, because you can directly reach. Sometimes if you use that intermediate by using adding these two edge weight is also, sometimes it may be less than the direct thing. So our aim is you have to minimize the distance. So that's why we are considering all the possibilities. So this is what the required recurrence. So first you have to construct a sequence of distance matrices. Okay, by applying this recurrence equation. So let us solve this with one example. This is what the given diagram. So obviously it should be a directed graph and edge weight is also. Okay. So D0. So I have already told that 0 indicates that it doesn't use any intermediate vertices. So the D0 initially represents the given weighted adjacency matrix. So this is the number of vertices 1, 2, 3, 4. Here 1, 2, 3, 4. So adjacency, that is 1 to 1 is 0. Okay. So from 1 you can directly reach 3 alone. Okay. So you cannot directly reach 2 or 4. Okay. So that's why the 1, 2, 3 is 3. Okay. So whereas the remaining values are infinity, which means that from the vertex 1 you can able to reach only the vertex 3 at the moment. So the vertex 2 and 4 cannot be reached at this moment. Okay. The next, when you come to 2, okay, so from 2, okay, you can reach 1 at a distance of 2. Okay, 2 comma 1. 2 comma 2 is 0. At the moment, you cannot reach directly from 2 to 3 and as well as 4. That's why it is infinity. Okay, so it's simply an adjacency matrix. Okay, in the usually adjacency matrix we'll use 1 or 0, but here it is a weighted matrix. So if it is an adjacent, simply you represent what is the edge weight. So it is D0. So next you have to construct the next distance vertex, that is D of 1, which indicates 1. You can maximum use 1 intermediate vertices to find the shortest path from every pair of vertices, that is 1 to 2, 1 to 3, 1 to 4, 2 to 1, 2 to 3, 2 to 4 likewise. So the one tip is the boxed row and column. The boxed row and the boxed column is used to find out what is the value of this D of 1. Okay. So you have to add these two values. Okay. In order to change these columns. Okay. So these value you are not supposed to change. Okay. So that is boxed row and column value. So the remaining can be altered. So when you come to this value, you look at this, what is the value in its row and column in the corresponding box. If you modifying this row, for example, you cannot able to modify this because it is 0. So when you come to this infinity, listen. So here the corresponding value in its boxed row is 3 and its boxed column is 2. So you add these two values. So 2 plus 3 is 5. So you compare with this previous value. What is that previous distance is infinity. So when you compare these two, which is minimum 5. So that's why this is that the distance between 2 to 3 is 5, which means that at this moment when you are using one intermediate, you are make use of this one as an intermediate vertex. Okay, so 2 plus 3, that is 5. You can reach 2 to 3 by using this intermediate vertex 1. Okay, that is 5. Again, when you come to this thing, the corresponding row value is infinity, here 2. So obviously you cannot able to change. Again, when you come to this 7, okay, so here also infinity, here also infinity, there is no change. Again 0, nothing. When you come here, here infinity, so there is no change. When you come to this infinity also, here 6, here 3, infinity, no change. When you come here, okay, come to this column, here the corresponding boxed column value is 3. Row value, column value is 6. When you add these, 6 plus 3 is 9. So 0 as such. Okay. So again this means that the vertex 4 to 3. 4 to 3. Okay. So at this moment when you are using only one intermediate vertex, that is 6 plus 3, 9. By using 1 as an intermediate vertex. Okay, so you have to make use of this boxed row and column to find out what is the value of D of 1. Okay, so you have to change these values alone. So don't change this 0. Okay, don't change the values zeros. Okay, so the next D of 2. So D of 2 can be find out the value of from D of 1. So again you have to mark the first row, first column. Okay, make use of these values to find out this. Again, you are not supposed to change this 0. Okay, so when you try to alter this value, look at this corresponding value over here is infinity. The corresponding row value is 5. So there is no change. 3. Again, here infinity you cannot able to change. Okay, so 205 is infinity, that will come as such because you cannot able to change. Again, when you take this value infinity, the corresponding value here is 7, here is 2. So 2 plus 7 is 9. The previous value is infinity. So that this value will be changed as 9. Which means that from vertex 3 to 2. 3 to 2. Okay. Again you are make use of this two intermediate vertices because 1 to 3 already you have find out that at a distance of 3. Okay. So again 3 to 2 is 6. So you can reach at a distance of 9. Okay. 3 to 1. 3 to 1 is 7 plus 2, that is 9. That's what we have added here. So that is this value. You look at this corresponding column value is 7, row value is 2. 2 plus 7 is 9. When you compare with this infinity which is smaller, so the 9. 7 as such, 0 you cannot modify, 1 you cannot modify. When you come to this 6, here infinity, here 2, there is no change. Infinity as such, 9, again here 5, here 6. So 6 plus 5 is 11. When you compare with the previous distance, it is 9, which is less. So that the 9 as such 0. So you have constructed D of 2. So again you mark the third row and third column to construct what is value of D of 3. So again 0 you cannot change. When you come to this infinity, the corresponding value is 7 over here. Here 3. So 7 plus 3 is 10. When you compare with infinity, that is less. So the 10. 3 you cannot modify. When you come to this infinity, here the box call value is 1. Column value is 3. 3 plus 1 is 4. Okay, the bold values indicates that the new distance is updated. 2, here 9, here 3. So 9 plus 3 is 12. So you cannot change. 0 as such. 5 you cannot change. When you come to this infinity, here box value is 1. Here box value is 5. 5 plus 1 is 6. When you compare with the infinity, 6 is less so that it is updated. Then again when you come over here, 9 you cannot change. 7, 0, 1 as such because it's a box value. When you come over here for 6, here the box value is 9. Here the box value is also 9. 9 plus 9 is 18. When you compare with the previous value, that is less. So 6 is retained as such. When you come to this infinity value, here the box column is 9. Row value 7. So 7 plus 9 is 16. When you compare with infinity, 16 is less. So that is updated. 9 keep as such. 0 you cannot change. So this is the value of D of 3. That is maximum uses 1 or 2 and up to 3. Either 1 or 2 or 3 as an intermediate vertices. Finally D of 4. So again you mark the fourth row. So here the fourth row under this fourth column. As again as such is marked as the first one. Okay. So you have to mark this. This is not. This is not, this row is not. You have to mark this fourth row and the fourth column. Okay. So 0 you cannot change. 0 you cannot change. When you come over here the 10. Okay. So here the box column is 4. Okay. And here 16. So 16 plus 4 is 20. When you compare with the previous value, 10 as such. Okay. So 3 you can, here you take 9, here 4. So again 9 plus 4 is 13. When you compare with, that is going to be the minimum value. 4 you cannot modify. So when you come to this value 2, okay, the box here is 6, here is 6. So 6 plus 6, 12. No change. 0 you cannot modify. 5 also, here 6, here 9, there is no change. So when you come to this 9, okay, when you come to this 9, here this corresponding value is 6. Here 1. So 6 plus 1 is 7. So when you compare with that previous value, the 7 is the minimum value, so that the 9 will be replaced as 7. Once again I will repeat. We are not going to consider this column, sorry, only this, okay, boxed. So when you come to this 9, you look at this, the row value is 6, the corresponding column value is 9. For 9 only you have to look into that, the corresponding row value, column value in its boxed row and column. So 6 plus 1 is 7. When you compare with 9, it is less, so that the 9 is replaced as 7. Then when you come to 7, here 1, here 16, no change. 0 you cannot modify, for 1 you cannot modify. Okay, so when you 6, 16, 0 as such, because this is boxed column. Okay, so this is what your required solution. Okay, so which means that from 1 to 2, okay, from the vertex you can reach the vertex 2 at a distance of 10. Okay, so 1 to 2, how you can reach 1 to 3, 3 to 2. So 3 plus 7 is 10. And from vertex 1 to 3, you can reach at a distance of 3. So that is direct. Okay, you can reach to 4 at a distance of 4. So that is this way. Okay, the next is 2 to 1. 2 to 1 at a distance of 2. 2 to 0, 3. 2 to 3 is 5. 2 to 3 is 5, no? So that is 2 plus 3, 5. So this is the, likewise you can able to write down this answer. The shortest path between 1 to 2 is 10, 1 to 3 is 3, 1 to 4 is 4. 2 to 1 is 2, 2 to 3 is 5, 2 to 4 is 6. Okay, so we have find out the all pair shortest path problem by applying the Floyd's algorithm by using the algorithm design technique, dynamic programming. Thank you.